Okay, let's start with the basics. Kubernetes, or Keats as it's often called, is a really important tool in modern software development. Basically, it's a system that manages containers for you. Think of it like a super efficient conductor for your applications. It takes care of deploying them, scaling them up when needed, and even fixing problems automatically. It simplifies things dramatically by managing deployments, scaling, and complex operations, all without needing constant manual intervention. Key concepts include pods, the smallest unit that can run your application, nodes, which are the work machines running those pods, and deployments that define what you want your system to look like. Okay, so let's start with the very basics, understanding how Kubernetes is built. Think of it like a complex city. At its smallest level, we have pods. These are basically tiny containers grouped together. They are the building blocks of everything you deploy. Then we have nodes, which are the actual computers or VM that run those pods. Now, there's a whole control center running on a special node called the master node or control plane. This is where things get interesting. The master node has several key components: an API server, which you use to talk to Kubernetes, scheduler, which decides where your pods go, and the controller manager, which constantly monitors and adjusts your cluster to keep everything running smoothly. Finally, we have services. They are like stable addresses that allow you to access your applications consistently, even if the underlying pod changes. Okay, let's start with the basics. What is a Kubernetes cluster? Imagine it like a really efficient team of computers all working together. Each individual computer in that team is called a node. These nodes can be physical servers, or they can be virtual machines running in the cloud. The heart of the whole operation is the control plane, which acts as the brain, making sure everything's running smoothly and managing resources effectively. And finally, we have pods. These are the smallest units that contain your application code. A deployment then ensures you have enough pods running to handle demand, and makes it easy to update your apps without downtime. Okay, let's talk about nodes in Kubernetes. Basically, a node is like one of the computers that makes up your whole cluster. It's a single worker machine. It could be a physical server or even a virtual one. Each node has its own set of components working together. There's the kubelet, which watches over your containers and makes sure they are running correctly. Then you have the container runtime, like Docker, that actually runs those containers. And finally, some networking tools to allow everything to talk to each other. Think of it this way: a node is just one piece of the puzzle in getting all your applications running smoothly within Kubernetes. Okay, let's talk about pods. They're really fundamental to Kubernetes. Essentially, a pod is like a tiny home for your containers. It groups one or more containers that need to work together closely. Maybe they share network resources or storage. They're designed to be easily managed and scaled, and you can think of them as the smallest unit you can deploy in Kubernetes. Okay, let's talk about pods and containers in Kubernetes. Containers are like individual shipping boxes. They hold all the stuff needed to run an application, making it portable and isolated. But a container alone isn't really useful on its own in a cluster. That's where pods come in. A pod is essentially a team of one or more containers working together. It's the smallest deployable unit in Kubernetes, and all those containers within a pod share resources like networking and storage. So, while a container is a single building block, a pod is how we group those blocks to create a complete application. Okay, let's talk about deployments in Kubernetes. Essentially, a deployment is how you manage multiple copies or replicas of your application pods. It's like telling Kubernetes, hey, I want 3 instances of this running, and it takes care of making sure that happens and keeping them updated even if you need to roll out a new version or just scale up as demand increases. Deployments work by creating what are called replica sets, which ensure the desired number of pods are always available. They're fantastic for managing updates and rolling back changes without interrupting your service. Let's dive into services. They're a really important concept in Kubernetes. Pods are super flexible, but they can disappear at any time. That's where services come in. They act as a consistent way to access your applications, kind of like a stable address for your app. Services use labels on the pods that make up your application and then automatically manage how requests get routed to those pods. It's all about providing reliable access even when things change dynamically under the hood. Okay, let's talk about services in Kubernetes. They are absolutely crucial for managing your applications. Basically, a service provides a stable IP address and DNS name for a set of pods. There are a few different ways you can create these services, each with its own strengths. You've got cluster IP, which is the standard and lets other services within the cluster talk to it using internal IP. Then there's node port, which opens up ports on every node, good for simple testing but usually not ideal for production due to security concerns. Load balancer automatically sets up a cloud provider's load balancer, giving you an external IP address. And finally, external name just maps the service to an existing DNS name. Think about what kind of access your application needs and that will help you decide which type is best. Okay, let's talk about the Kube API server. It's arguably the most important part of Kubernetes control plane. Think of it as the brain and main access point to the whole system. This component acts like a central front door, handling all requests from tools like Kubectl or other components within the cluster. It's responsible for managing everything, creating, updating, deleting your resources like pods and deployments. And importantly, it makes sure that only authorized users are able to interact with the system using its authentication and authorization mechanisms. Okay, let's talk about the Kube scheduler. It's a really important part of how Kubernetes works behind the scenes. Basically, when you create a new container or an existing one needs to be moved, the scheduler steps in and figures out where to run it. It acts like a traffic controller, looking at all the available nodes, those are your worker machines, and comparing what each node can offer with the requirements of the pod you're trying to deploy. It then makes a smart decision, taking into account things like resource constraints and any specific rules you've set up in your cluster, ensuring everything runs smoothly. Let's talk about the Kube Controller Manager. This is a really important piece of the Kubernetes puzzle. It's not just one thing, it's actually a collection of processes working together as the cluster's central control system. Imagine it like having a team of managers constantly checking and adjusting things to make sure everything is running as planned, whether that's keeping the right number of pods up and running, or making sure nodes are healthy. It handles tasks like maintaining replica counts for your applications, managing services, and even dealing with node failures all automatically. Okay, let's talk about ECT. It's a really important piece of the Kubernetes puzzle. Basically, ECT is like the cluster's memory. It's a distributed key-value store that keeps track of everything important about your Kubernetes setup, from the state of all your deployments to where services are running. Without it, Kubernetes wouldn't be able to understand what's going on or manage things effectively. It uses a clever algorithm called RAF to make sure all the nodes in the cluster agree on the same information, which is crucial for reliability. Okay, let's talk about stateful sets and deployments. Deployments are your go-to for stateless applications. Things like web servers or API-worthy order of pods doesn't matter as long as you have enough running. They handle scaling and updates smoothly. Now, stateful sets are a different beast altogether. These are designed for stateful caps sync databases or message queues that need to keep track of their data and ensure things happen in a specific order. Each pod in a stateful set gets its own unique name and stable network identity, which is really important when you're dealing with persistent storage. Think of it like this: deployments are about many-to-many, while stateful sets are about one-to-one, where each pod needs to be uniquely identified. Okay, let's dive into replica sets. They're really important for keeping your applications running smoothly in Kubernetes. Think of them as guardians of your pods. Essentially, a replica set makes sure you always have the right number of copies replicas of your application running. If one pod crashes or fails, Kubernetes automatically spins up another one to take its place, ensuring that your service stays available. They're fantastic for scaling if traffic increases. They'll add more pods, and they also make rolling updates and rollbacks really easy, so you can deploy new versions without any downtime. You define the desired number of replicas in a deployment or other similar resource. Let's talk about how Kubernetes handles load balancing. It's actually pretty clever. First, Kubernetes has its own internal DNS system. So, when you want to access a service, like my service, Kubernetes automatically figures out the IP address of one of the pods that's running it. This is super important because as your pods are created and removed, Kubernetes keeps track and updates this information dynamically. Now, by default, Kubernetes uses something called round robin. Basically, it rotates through all the available pods to distribute traffic evenly. But you can customize this. You can tell Kubernetes to use different strategies like least connections, which sends requests to the pod with the fewest active connections right now. It's important to remember that Kubernetes itself doesn't do traditional hardware-based load balancing. Instead, it leverages the features of your cloud provider or infrastructure, things like load balancers on AWS or Azure. Think of the service as a smart proxy, forwarding requests to healthy pods and ensuring everything runs smoothly. Okay, let's dive into config maps. Basically, they're like a simple way to store configuration information for your Kubernetes apps. Instead of hard-coding things like database passwords or API keys directly in your code, you put them in a config map, which is just a key value store. This makes updating those settings much easier because you don't have to rebuild and redeploy your application every time. It also helps with portability, so moving your app between environments becomes simple. Config maps are really valuable for keeping your deployments flexible and manageable. Okay, let's talk about secrets in Kubernetes. Basically, they're how you securely store sensitive information like passwords and API keys, things you absolutely wouldn't want lying around in plain sight within your pods. Directly embedding these into your deployments would be a huge security risk. Kubernetes uses secret objects, which are just files holding the data, but crucially encrypts them at rest using ICT, so even if someone gets access to the cluster's database, your secrets stay protected, and you control who can actually use those secrets through Kubernetes RBAC system. Finally, Kubernetes lets you dynamically inject these secrets into your pods as needed, so each pod only has what it needs, which is a really good practice for keeping things secure. So, you've got your pod running awesome. But how do users outside the cluster get to it? The key is exposing that pod. Kubernetes offers several ways to do this, with services being the most common. There are three main service types: cluster IP, node port, and load balancer. Cluster IP keeps things internal, accessible only within the cluster. Node port opens up access on every node's IP address, handy for testing but potentially less secure in production. And finally, load balancer provisions a cloud load balancer, giving your service a public IP address. Let's look at node port as an example. It's easy to set up and exposes the service on all nodes, though you need to make sure no other application is using that port first. Okay, let's talk about namespaces in Kubernetes. Basically, they're like creating separate rooms or folders inside your main cluster. They aren't physical separation, you don't need different servers, but they create logical boundaries for all of your resources. This is super useful when you have multiple teams working on the same cluster, or if you want to keep your development and production environments completely separate. It helps prevent conflicts and makes resource management much easier. Okay, let's dive into scaling applications within Kubernetes. There are a few really important ways we do this. The most common is horizontal pod autoscaling, or HPA. It's like having an automatic workforce that increases or decreases based on how busy your application is. We monitor metrics like CPU usage or memory, and when things get too heavy, HPA spins up more pods to handle the load. Then there's vertical pod autoscaling, which focuses on adjusting the resources inside each pod. Think of it as giving them bigger disks if they need more space. Finally, you can manually adjust the number of replicas in your deployment, but that's generally less flexible and requires you to constantly monitor things yourself. Okay, let's talk about scaling your Kubernetes deployments. We often hear about autoscaling, and there are two main types: horizontal and vertical. Horizontal pod autoscaling, or HBA, is all about adding more pods to handle increased demand. It's like having a team grow when you need more hands on deck. Vertical pod autoscaling, on the other hand, focuses on tweaking the resources assigned to individual pods, specifically their CPU and memory limits. It's like giving each worker pod more or less horsepower depending on what they're doing. HBA scales out, while VPA scales up within a deployment. Understanding when to use each approach is crucial for maintaining optimal performance and cost efficiency. Okay, let's talk about daemon sets. Think of them as the always-on helpers in Kubernetes. Sometimes you need a specific process running on every single node in your cluster, things like monitoring tools or logging agents. If you just create a regular pod and deploy it, it only lives as long as that deployment is healthy. But if the deployment fails, those pods disappear, and your nodes suddenly stop working properly. A daemon set solves this problem by ensuring there's always at least one copy of your desired application running on each node. They use node affinity to decide where to deploy these pods, and Kubernetes takes care of managing their lifecycle, restarting them if they fail, scaling them up as needed. It's like having a dedicated assistant for each server. Okay, let's talk about jobs and cron jobs in Kubernetes. They are both related to running tasks, but they do things differently. A job is like telling Kubernetes do this one thing, and then stop. It creates pods, gets them to run the task, and once it's finished, those pods are gone. It's great for things you only need to do once, such as a database migration or generating a report. Now, a cron job is like setting up a recurring appointment for Kubernetes. Think of it as do this job repeatedly on the schedule. You can tell it to run every hour, every day, whatever you need. It's perfect for tasks that need to happen regularly, like backups or data synchronization. The main difference? A job runs just once, while a cron job runs over and over again according to your set schedule. Okay, let's dive into persistent volumes. They're super important for any Kubernetes deployment that needs to keep track of data. Think of a PV as a general storage pool within your cluster. It's not a specific hard drive or USB stick, it's more like saying, hey, there's this much storage available here. Unlike temporary volumes, data on a PV sticks around even if the container that uses it gets restarted or deleted. A PV describes the size and how you can access the storage, whether it's read-only for multiple pods or writable by only one. And finally, when the PV is removed, what happens to the data? That's determined by a reclaim policy. The important thing to remember is that Kubernetes manages these PVS, but the actual data itself is handled by another object called a persistent volume claim. Okay, let's dive into persistent volume claims. Think of them as the key to managing your persistent data in Kubernetes. Basically, a PVC is a request for storage, like saying, I need a certain amount of space and with specific access permissions. It's a way to abstract away the complexities of finding and using actual storage volumes within the cluster. You have persistent volumes, which are the real physical storage resources, and then the PVC itself describes what you need. A pod can then use this volume as if it were a regular file system. Okay, let's talk about storage in Kubernetes. It's a surprisingly complex topic. Basically, Kubernetes doesn't ** any storage itself, it just asks for it. You have persistent volumes, which are like general concepts of storage capacity within your cluster. Then you make requests for that storage using persistent volume claims, kind of like making a reservation. Storage classes then define how those volumes actually get created, whether they're provisioned automatically or manually. And Kubernetes uses dynamic provisioning to handle the creation and deletion of these volumes based on your claims. There are tons of different storage providers you can use, from cloud provider solutions like AWS, EBS, all the way down to local disks if you're running a single node cluster. Okay, let's talk about labels and selectors. They're seriously important in Kubernetes. Think of labels as little sticky notes you attach to your pods, deployments, or any other resource. They are just key value pairs like app equals my app, environment equals production, or team equals DevOps. These labels help you organize and categorize everything. Then, you use selectors, which are also key value patterns, to find specific objects based on those labels. Essentially, the selector says find all the things that asterisk have asterisk these labels. For example, a deployment might use a selector to only manage pods labeled app equals my app and environment equals production. So labels define information and selectors use that information to target resources. Okay, let's talk about ingresses. Basically, they're like the main gateway for your applications running inside Kubernetes. Instead of having a different IP address and port exposed for every single service, an ingress provides a single point where traffic from outside your cluster comes in. It smartly routes the traffic to the right service based on things like the domain name you're using or the URL you're requesting. It simplifies accessing your services and often includes load balancing and even SSL termination, making it much more manageable than exposing each service directly. Okay, let's talk about rolling updates, a really important concept for deploying changes to your Kubernetes applications without interrupting your users. Basically, it's like gradually swapping out older versions of your application with newer ones. Think of it as a slow and steady replacement, ensuring that you always have at least one version available to handle traffic. First, you modify your deployment spec, maybe adding some new features or bug fixes. Kubernetes then scales up the number of pods based on that new spec. Then older pods are gently shut down and fresh pods are created to take their place. This process repeats until everything is updated. It's all about minimizing downtime and making sure your users keep getting access to a working application. Okay, let's talk about rolling back a deployment in Kubernetes. It's a really important skill to know for an interview. Essentially, it means going back to a previous version of your app. Kubernetes makes this pretty easy thanks to its deployment objects and their rolling update strategy. The most common way to do it is with kubectl rollout undo. This command targets the latest revision and reverts you to a specific past one. You'll need to find out what that revision number is using kubectl rollout history. It lists all the versions of your deployment. Keep in mind that Kubernetes keeps track of these revisions, so you have options. There's also a less common method of manual deletion and recreation, but it's generally best to stick with the automated approach. And always remember, testing rollbacks in a non-production environment is key. Okay, let's dive into Helm charts. Basically, they're like package managers for Kubernetes. Imagine you have a complex application, lots of microservices and databases. Without Helm, deploying all those resources to your cluster would be super complicated and time-consuming. A Helm chart is a blueprint that tells Kubernetes exactly what to do, which pods to create, how to configure them, and even how to handle updates. Inside a chart you'll find templates written in YAML. These define the desired state of your application, plus reusable components called charts and a way to customize everything using values. It really simplifies deploying and managing your Kubernetes apps. Okay, let's talk about the sidecar container pattern. Basically, it's like having a helpful assistant for your main application. You have your core app container doing its job, and then you add a sidecar container alongside it. This sidecar doesn't do the main work of the app. Instead, it handles things like logging, monitoring, or security tasks that are important but aren't part of the application itself. Because they share the same network space, the main app can easily communicate with the sidecar to send logs or get metrics. It's a really useful way to keep your applications clean, modular, and easy to manage. Okay, so let's dive into readiness probes. They are a really important part of keeping your Kubernetes applications running smoothly. Think of it like this: liveness probes just tell Kubernetes that a container is still alive, it hasn't crashed. But a readiness probe goes further. It asks, is this thing actually ready to handle requests from users? It checks things like database connections or if an API endpoint is healthy. If the probe fails, Kubernetes smartly takes that pod out of service temporarily until it's back up and running properly, ensuring users aren't getting served by a faulty app. Okay, let's dive into liveness probes. They're super important for keeping your apps running smoothly in Kubernetes. Think of them as a health check that constantly asks, is this container still alive and kicking? They don't look at whether a request succeeded or failed, they just want to know if the underlying process is functioning correctly. If a probe keeps failing, Kubernetes knows something's wrong and will automatically restart the container. You define these probes within your deployment configuration. You can check for HTTP requests to a health endpoint, try connecting with TCP, or even run a command inside the container. It's all about detecting problems so Kubernetes can take action. Okay, let's talk about taints and tolerations. They are all about controlling where your pods can run in Kubernetes. Taints are like warnings you slap on a node, saying, hey, be careful, there might be something undesirable here. They come in the form of a key, an effect like telling pods not to run or prefer not to run, and a namespace. Now, tolerations are the antidote. They are part of your pod definition that say, I know about this warning, but I still want to schedule myself on this node. Essentially, they tell Kubernetes, don't care about the taint, I can handle it. Okay, let's talk about node and pod affinity. They are both ways to influence where your Kubernetes pods run. Node affinity is like saying, this specific pod must be on this particular node, often based on things like hardware specifications or dedicated resources. It's a hard requirement. Then there's pod affinity, which is more about grouping related pods together. These two pods should ideally run close to each other. It's a preference, not a strict rule. You can use labels to define these affinities, and Kubernetes will do its best to fulfill them. Okay, let's talk about how Kubernetes knows where your applications are running. The key idea is using what we call services. Services act like stable addresses for your apps. They hide the fact that your application might be spread across multiple pods. Basically, when a client wants to connect, it doesn't need to know which specific pod it's talking to. Instead, it just uses the service name, and Kubernetes handles the rest. It all starts with DNS. Kubernetes has its own internal DNS server, the kube DNS or core DNS, that keeps track of all services in the cluster. When a client tries to find a service, it asks this DNS server for the address. And here's the really clever part. Kubernetes constantly monitors the pods associated with each service. If a pod goes down, the service automatically updates its list of healthy endpoints and redirects traffic accordingly. This ensures that your applications are always available and efficiently utilizing resources. Okay, let's talk about Kubernetes annotations. Basically, they're like extra notes attached to your resources, pods, deployments, services, whatever. They're different from labels. Labels are for finding things in your cluster, while annotations are more for providing context and information. You can think of them as little hints or descriptions. For example, you might use an annotation to track who created a pod, what environment it's running in, or the version of the application. Tools and even custom operators can read these annotations to help automate things and make your cluster management smoother. Okay, so let's talk about the kubelet. It's really the heart of what makes Kubernetes work. Imagine each node in your cluster that's a computer running Kubernetes, and on every one of those nodes, there's a kubelet. The kubelet is like a little helper for your containers. It keeps tabs on them, making sure they're actually running as you defined them, and it lets the control plane know if something goes wrong. Basically, it's responsible for ensuring the health and proper functioning of all those containers on a particular node, a really important job. Okay, let's talk about the core idea here, container orchestration. Imagine you've got lots of little containers running your application, and they each need to be managed separately. That can get really complicated quickly. Container orchestration is basically a system that takes care of all those individual containers for you. It's like having a conductor for an orchestra. It makes sure everything runs smoothly, scales up or down as needed, and keeps everything healthy. Kubernetes is the most popular tool doing this job today. It automates deployment, scaling, health checks, resource management, basically anything you'd normally do manually when managing your containers. Okay, let's talk about the difference between Docker Swarm and Kubernetes. Docker Swarm is essentially Docker's built-in clustering solution. It's really easy to get up and running if you already know how to use Docker commands. It feels very familiar. However, it's best suited for smaller projects and teams that don't need a ton of advanced features. Now, Kubernetes, or Keats as it's often called, is a much more powerful and complex system created by Google. It can handle huge deployments and has tons of cool capabilities like automatic scaling and self-healing. But be warned, it does have a steeper learning curve. Think of Docker Swarm as the simpler option for smaller needs, while Kubernetes is designed to tackle bigger challenges. Okay, let's talk about securing your Kubernetes cluster. Interviewers will want to see that you understand how to build a robust security posture. There are several key areas to focus on, starting with network policies, which control the flow of traffic between pods and really limit what can get in or out. Then we have role-based access control, or RBAC, which is about giving users and services only the permissions they absolutely need. Next up, secrets management. This is crucial. You never want to hardcode passwords or API keys into your deployments. Instead, use Kubernetes secrets or integrate with a dedicated tool like HashiCorp Vault. Image security is also important. Regularly scan your container images for vulnerabilities before deploying them. Okay, let's talk about RBAC. It's basically Kubernetes' way of controlling who gets to do what inside your cluster. Instead of giving someone broad permissions directly, you define roles that bundle specific actions like reading, creating, or updating resources, and then assign those roles to users or service accounts. Think of it as a permission system based on what people are allowed to do, not who they are. It's all about following the principle of least privilege, which means giving people only the access they need, making your cluster much more secure. Okay, so monitoring a Kubernetes cluster is all about getting the right information at the right time. First, we're gathering metrics, things like CPU usage and memory consumption, using tools like Prometheus. Then, we need to collect logs from every container and node to see what's happening under the hood. Setting up alerts based on these metrics or unusual log patterns is super important, so you know immediately when something goes wrong. Don't forget health checks. Kubernetes uses probes to automatically check if pods are healthy, and monitoring those is key. And for really complex applications with lots of microservices, distributed tracing can be a lifesaver in figuring out where problems are hiding. Tools like Prometheus, Grafana, and Elasticsearch are commonly used to manage this whole process. Okay, let's talk about how we keep tabs on our Kubernetes clusters. We generally look at three main areas: metrics, logs, and events. Metrics are just numbers, things like CPU usage, memory consumption, and network traffic. Tools like Prometheus and Grafana are super common for collecting those metrics and visualizing them in dashboards. Then there's logging, which is all about capturing text-based records of what's happening inside the cluster. The ELK stack Elasticsearch, Logstash, Kibana is a really popular choice here. And finally, we need to track important events like when pods are deployed or scaled, or if something goes wrong. Kubernetes audit logs and webhooks can help us capture these events. Okay, so Kubernetes is fantastic at managing things like regular deployments and services, the standard stuff. But what happens when you have a really unique application or a specific configuration that isn't covered by those built-in objects? That's where custom resource definitions come in. They're basically like adding your own extensions to Kubernetes, allowing you to define and manage entirely new types of resources. Think of it as creating your own API for Kubernetes. You tell it what information these new resources should have, and then you can start managing them just like any other Kubernetes object. This is super important because it lets us build more complex automated management systems using something called operators. Okay, let's talk about load balancers in Kubernetes, specifically the difference between internal and external ones. Internal load balancers are like a private hallway inside your cluster. They allow services within the same namespace to easily talk to each other. Kubernetes handles all of this automatically for you. It's super convenient. Now, when you want users from outside your network to access your application, that's where external load balancers come in. These are connected to your cloud provider's load balancing services like AWS or Google Cloud, and they act as a gateway, directing traffic to the right pods inside your cluster. The main difference is simply who can access them. Internal load balancers are for within cluster communication, while external ones open up your application to the world. Okay, let's talk about how we handle updating configurations when things change in Kubernetes. The most common and recommended method is rolling updates. This lets you gradually roll out new versions of your deployments with minimal downtime. You can also use config maps to store your configuration data, which makes it super easy to update and reuse across different services. For secrets like passwords or API keys, we use a separate mechanism secrets, and they behave similarly to config maps when it comes to updates. Tools like Customize and Helm charts help us manage more complex deployments and apply changes consistently across various environments. The key is always using declarative configuration, telling Kubernetes exactly what you want and making sure those changes are idempotent, meaning applying them multiple times has the same result as just applying them once. Don't forget to test everything in a staging environment first. Thank you for watching.